And now we have the first plenary talk of this conference, and it will be given by the fresh laureate of Loman Holography Award, Professor Joseph Rosen from Ben-Gurion University of the Negev, Israel, on the topic of advanced imaging tasks using phase-only spatial light modulators. So please, the floor is yours.
Good morning. Let me open my talk with acknowledgements. So first, I'm grateful to Springer Nature Group and Professor Mackenzie for awarding me the Luhmann Holography Award of 2025. University of Tartu, Professor Asser and Professor Yogi for hosting this wonderful event, and the conference organizers, Professor Anand, Tia, and Arvin, and Luhmann's family representative, Judge Reidemaker. And now I couldn't achieve any award or any scientific achievement without the help and support of my colleagues and PhD students. Some of them are shown here, and some of them are here today. Of course, Professor Anand, Professor Shaked, and Professor Kumar. I'm grateful to all of them for helping me to achieve what I achieved. Okay, my talk today about advanced imaging tasks using phase-only spatial light modulator. This is the outline of my talk. I start with a brief introduction about holographic imaging, and then I will mention Finch, Fish, Fourier, incoherent holography, and Coach, coded aperture holography. And then we have one work of combining the two concepts together, Coach and Finch. And then I will move to a few applications: 3D imaging and sectioning, depth of field engineering, improving the image resolution, and non-invasive imaging through a scattering medium. So we start with this table about the context of our work in the topic of holography for imaging. We divide it to a table where the columns are the mode of object illumination. So we have two modes, coherent or incoherent illumination. And the lines are the mode of hologram reconstruction. So we have optical reconstruction or digital reconstruction. And now we show a few examples of each quarter. So the first invented hologram belongs to optical coherent hologram, published in 1948 by Denis Gabor, and the setup is shown here. In the optical incoherent hologram, in 1965, in two separate papers, one by Cochran and one by Peters, they proposed the self-interference holography. And interestingly, in 1970, Braindal and Luhmann, the hero of today, analyzed the self-interference holography in a paper published in 1970. In the digital holography invented by Goodman and Lawrence in 1967, we see here the on-axis digital hologram with phase shifting process proposed by Yamaguchi and Zhang in 1997. And our contribution belongs to this quarter, where we see the digital incoherent hologram, first proposed by Poon in 1985, the optical scanning holography, and our contribution published in 2007, the Fresnel incoherent correlation holography, which is based on all these four setups. So we use on-axis setup like Gabor, and we make use of phase shifting procedure. We also, our setup is based on self-interference holography, and we demonstrate a Fresnel hologram like the optical scanning holography. We also make use of SLM, spatial light modulator, phase-only spatial light modulator, shown here. So we have here a liquid crystal display, and the mask on the display is created in a computer, and the mask modulates the incident wavefront such that we get a curved wavefront in the reflected beam. And this is also connected to the seminal work of Professor Luhmann. He is known best for the invention of computer-generated hologram, shown here, and the original setup from 1967 is shown here, when he created a binary hologram by the computer, not the same computer. We didn't have PC in 1967, but anyway, the computer-generated hologram is positioned in the front of a spherical lens, illuminated by plane wave, by laser beam, and the reconstruction, the letter E, is obtained in the back focal plane of the lens. And it is quite different, it's quite similar to our setup, where we put the SLM in the aperture of an imaging system, illuminated it by a point object, and get intensity on the camera, which is physically similar to Luhmann's demonstration. We both get intensity, which is relative to magnitude square of the two-dimensional Fourier transform of the mask. So in both cases, but the mask is different, but the physics is the same. He used a binary amplitude static phase, and we today use multi-level phase mask and dynamic mask. So this is the difference because of the progress of technology. Okay, so back to the Finch. On the SLM, we multiplex two phase masks. One is a diffractive mask, one is a planar mirror, and from each object point we get two waves, two beams. One is focused, one continues as a plane wave, and because they are mutual coherent, we get interference between them, and we need to eliminate the twin image and the bias, so we do it by phase shifting, 3 shots, each one with a different lens with different phase value, and we get the complex valued hologram, and from that we can reconstruct each letter O, S, and A in a different Z location. So this is the first Finch, and now we can jump to 2024, and we see here a setup of single-shot Finch. This project headed by Professor Leon Zhang, and the SLM is the same, but the multiplexing is what is called polarization multiplexing. We have two beams from output out from the SLM, two orthogonal polarization, and we split them to 4 row holograms shown here and displayed and recorded by 2 cameras. And each row hologram, the phase difference between the orthogonal polarization is different. So in one shot, we get 4 row hologram, can make the superposition of the phase shifting and get reconstruction. And because it's fast, only single shot, we can take a video movie of 2 objects in focus in different slices, different sections. One is the cube in slice 1, and the other is this rows in slice 2. And if they are changed dynamically, we can follow it because it's a single shot. So we see it here. Okay. We continue with optical sectioning. Now the goal is to get only one in-focus image and to eliminate the out-of-focus images. So we take Finch with the polarization multiplexing. We get 2 images in orthogonal polarization, and we put a second SLM, the same phase, only SLM, but we display on the second SLM what is called phase pinhole. We see here the pinhole, and we scan with the phase pinhole all the plane and record many holograms between these 2 points, such that all the rest of intensity before and after this plane is eliminated. So we see it here. 2 overlap objects, the resolution chart with 16 line per millimeter and 18 in a Finch before the sectioning, and after scanning with the pinhole all the plane, we have only the in focus 16 and in another plane the in focus 18 due to this sectioning progress. With 2 SLM, we can convert Finch hologram, Fresnel hologram to Fourier hologram by displaying 2 different spherical lenses on each SLM. The SLM is active the 2 SLMs are active in 2 different orthogonal polarizations. This is active for the light for the vertical polarization, and this is active to the horizontal polarization. And by this setup, we create 2 images on the same plane. One is rotated by 180 degrees compared to the other, and this gives us a Fourier hologram. This is a reconstruction after only 2 shots, and this is after 3 shots. And if we turn off this SLM, we get back to the Fresnel hologram, and the reconstruction is shown here. We can also make it all set up in one line with 2 SLMs, and we also can reconstruct 3-dimensional scene. We see here these two objects are in focus, and here this one is in focus, and in this case the conjugate image here is in focus. And again, if we turn off the second SLM, we go back to the output of Fresnel hologram of the Finch, where this is in focus, and here is the last object is in focus. And if we go back to the setup of Finch, we see here the optical side, and now we want to generalize it, and we want to create what we call coded aperture correlation holography. So we do two steps. First, we replace the lens, the diffractive lens mask, with some random mask, and we change the digital reconstruction inside the computer, shown here. So it looks like here. This is a work from 2016 with Professor Anand. And we have here 3 random masks, and the reconstruction is done by a library of point spread holograms. Each one is a response of a single point along the z-axis. So this library enables us to reconstruct each section in the 3-dimensional volume. And a year later, we continue to generalize, and we remove the interference. It is called interferenceless coach, a setup without interference, with a single phase mask. We create a single chaotic wavefront, and this wavefront is sensitive to the location, to the 3-dimensional or to the z location of the object. And the reconstruction is still by the library of point spread hologram. So we see here the process. We have object. We take what we call object hologram, and we cross-correlate it with the library, and one correlation with one of the members produce the reconstruction, and according to the location of the point spread hologram, we know where is it, what is the z distance of the object. And we see here the results, 3 sections of a LED, and resolution chart, 2 resolution charts in different planes. And we see that we have in plane 1, this is in focus, in plane 2, another resolution chart in focus, and we compare it to imaging system with a zoom lens, and the results are similar. When we continue and compare the resolution properties of 3-system coach, Finch, and conventional imaging, we see that Finch has a longer depth of focus, and here we see the graph of the point response of Finch. It is much wider than the curve of coach and conventional imaging, and we see it here. The autofocus image in Finch looks much stronger than the autofocus of coach and conventional imaging in both planes. On the other hand, if we take a cross-section of one of the grating, we see that the visibility of Finch is greater than the visibility of coach and regular imaging, indicating that the the lateral resolution of Finch is better. So in 2021, we try to combine the 2 systems, Finch and coach, to a single system that has resolution of Finch, lateral resolution of Finch, and axial resolution of Coach. And the idea is to create, to display on the SLM a mask that create randomly distributed dots. And for each dot, we have we create the twin dot, and we create locally a Finch pattern for each pair of dots. So we see here the output. We call it a coded aperture with Finch intensity response, CIPHR, in short. So the CIPHR results are shown here. We have the 3 row holograms of a point, 5 dots, and for each on each dot we have a Finch response shown here. And here is the object hologram superposition in the computer. We get phase and magnitude of the hologram, and we can reconstruct it. And we see that first the lateral resolution of CIPHR is similar to the lateral resolution. We see the depth of modulation, or the visibility of the grating is bigger or greater than that of direct image. And the axial resolution, if we check it for, we see the out-of-focus image in the case of CIPHR is weaker, much weaker than the out-of-focus of Finch, and similar to the out-of-focus of direct imaging. And the graphs are shown here. Indeed, CIPHR and direct imaging have a better axial resolution than Finch. And Finch and CIPHR, the red and the green, have visibility greater than the visibility of the blue line, which is the direct imaging. Depth of field engineering, we can take the concept of ICAPI to design a 3-dimensional point spread function such that in every subvolume we get different distribution of random dots, and by that, if the image is around 0.1, we can reconstruct only this image by this set of PSF, by this point spread function. However, if the object in 0.2, we still can reconstruct it by a different point spread function, and we can reconstruct both images if we want. Everything is post-processing after taking the hologram, and it's a single shot hologram. And we see here the results for for several number of dots. If we concentrate on the 9 dots, we see here the object hologram, the one-shot object hologram. And now in the computer we can reconstruct the far object here by one PSF, the close object in a different PSH, or both objects by combining the two PSF together. Improving the resolution by SLM, and here we use the dynamic property of the SLM. We take a regular imaging system, put the SLM in the aperture, and on the SLM we display few different phase masks. And for each phase mask, we take 2 images. One is the blurred image of the object, of this butterfly, and we measure the point spread function. We make deconvolution between all the pairs, object and PSF, and we average over all the deconvolution, and by that we reduce the noise and improve the resolution. So we see here the results. Here we have a simple direct image, and the group 6 cannot be resolved, the lower group here, the lowest group here, and here we see the PSF. After we know the convolution of one image, we still cannot resolve group 6. Even if we take a K shots without the SLM, without the phase, and then we average over all the winner convolutions, still group 6 cannot resolve. However, in this image, we changed 20 times the phase on the SLM and average over all the deconvolution, which was a nonlinear deconvolution, and we could resolve the group 6 this time. And finally, the last application is a non-invasive imaging through scattering medium, again with the phase only SLM. It is based on a paper by Katz et al. From 2014, where they proposed to take the blood pattern from the scattering medium to make autocorrelation of this blood image, and by that the results of the autocorrelation is autocorrelation of the object, convolution with the delta function plus some bias, some constant. If we remove the constant and make a Fourier transform, we get a magnitude square of the Fourier transform of the object, and by phase retrieval we can reconstruct the object. So our contribution from 2019 was to project the scattering, the blurred image on SLM. On the SLM we put two different random masks. So first, by subtracting the two images, we eliminate the bias. We need to eliminate the bias, and we get a sharp delta function, like here. And additionally, we can change the phase mask many times as we wish and average on the results, and by that improving the phase retrieval algorithms. And we also show that we have control on the resolution of the image. And here we see the results for digit 2. We took 25 experiments of phase retrieval and averaging over them and got the digit 2, and the same thing for the digit 6. So, conclusion of my talk. SLM can be used for various operations, and we show wavefront modulation. We show here beam splitting in the case of holography, two-wave interference. We also can change, with the SLM, we can change the phase between the two beams and get and execute the phase shifting procedure. And SLM can be used for many applications, such that we see here Finch, Fish, Coach, all the three-dimensional digital holograms can be done with the SLM. Dynamic, we can do imaging, 3D imaging sectioning by the dynamic phase pinhole. We can improve the resolution. And finally, we can improve the algorithm of non-invasive imaging through scattering medium. And the final conclusion is that the SLM is a powerful device, and it can be even more powerful if the technology can be improved by giving more pixels, improving the resolution of each pixel, and producing phase SLM in a transmission rather than in a reflection mode. Thank you for your attention.
Thank you. Now we have time for the questions, so please. Aha, one is from there.
Thank you, Professor Rosen, for your presentation. My question is about how long does it take to record, let's say, full field of view of images, and how long does it take to do the processing of them to get the final results that you presented here?
In which application?
So let's say the one that you have with the two random masks, that you subtract the background from the experiments.
In the imaging through scattering medium, you mean?
Previous of that. So if you, okay, there, no.
This one?
No, after. There. So you said that you record two, to subtract the background, you record two images with different masks. And so you subtract one from the other one to get rid of the background.
So it can be in a rate of video. It depends on the rate of changing images on the SLM, and I mean it's something that should also be improved. The dynamic rate of SLMs, they are not so fast now, but if they will be improved, we can take as fast as the technology can allow us. Okay?
Yeah, thank you so much.
Thank you. So, more questions?
Thank you very much, Professor, for your excellent talk. I have the question because recently there is a lot of talks among the producers of SLMs and LCOSs. Is it any advantage if it is possible to produce amplitude phase
together?
Spatial light modulator? Because really for holography, if we have these, then we can simplify a lot of techniques and a lot of imaging. So in your techniques, would you see the advantage if you have in hand high resolution, phase amplitude spatial light modulator? Would it help in your techniques?
I don't think, because if amplitude SLM absorbs the light, so I always and because we have a lot of losses of optical power, I prefer to work with the phase-only SLM because they naturally, inherently don't absorb the light. And I don't see anything that we can achieve if we also modulate the amplitude. So I prefer to have a transmission mode phase only SLM rather than, let's say, a reflection mode phase plus amplitude SLM. I don't see any advantage by modulating the amplitude. But it's personal view.
We have next question.
Thank you, Professor Rosen, for a very interesting talk. My question is related to specifically this that you just mentioned. why do you prefer a transmission mode SLM than the reflecting one? Is just because it's easier to make the optical setups, or will you gain some optical efficiency in the experiments as well?
Yeah, I think the efficiency will be improved if we look on this system. We don't use we don't use beam splitters here, but there is an aberration by the tilt of the incident light, and when we make it orthogonal incidence, we have to use beam splitter, and we lose a lot of light. So transmission mode SLMs will solve these problems.
Thank you. We have next question.
So Professor Rosen, I have a small query. It's about the non-invasive imaging through scattering media. You did for only two-dimensional object, or also did for three-dimensional?
Again. What is your question again?
So object was, the image object is only two-dimensional, or it's a three-dimensional object? The object behind the scattering media.
In this case, it was two-dimensional imaging, but in a different project, actually the three-dimensional project we did was invasive imaging. The project of non-invasive imaging was only with a two-dimensional object.
Okay, thank you.
Thank you very much. Congratulations for award. So I have a different kind of question. So, what the trigger of you finding a finch? So you have you have the first paper 2007. So before write your paper, you find out of you found the finch method in your head. What kind of trigger of your finding?
What kind of?
Trigger. Why did you find your method? You understand?
Okay. At that time, we've been busy with scanning holography. I started the project in Brucker's lab. We got money to improve the scanning holography, but it is very slow method. So we looked for a way to do Fresnel holography. Fresnel means convolution with quadratic phase function, but without the scanning. So this was a trigger. The trigger was to find an optical correlator that can make correlation between general object and quadratic phase function. That's what I remember.
Thank you very much.
More than almost 20 years.
20 years.
Yeah, since then.
Thank you for your talk. I had a question. Since you're using SLMs, it's very sensitive to the polarization. So does that limit the kind of objects you image, or did you see is there some constraint because of using the SLMs?
It gives us the advantage of the ability to multiplex different masks for the different waves. Without this property, we cannot. We have to go back to the spatial multiplexing, like the first finch. And the disadvantage of spatial multiplexing is that you get a noise because you have random pixel belongs to one mask and random pixel to the other mask, and the result is a reconstruction, but with a lot of noise. So this polarization property of the SLM is a big advantage.
Okay, more questions? One is in there. Okay.
Congratulations on the Roman Award, and I would like to I'm impressed your presentation. So related to Professor Hayaseki's question, I would like to know why you try to capture the incoherent holograms, not only spatially but also temporary incoherent holograms. In the first publication of the Finch in 2007, you use the arc lamp and you capture the spatially and temporary incoherent holograms using a lamp. Why you tried? This is because liquid crystal spatial light modulator has wavelength dependency. However, you tried. Why you tried? I would like to know your motivation.
I didn't understand of using what?
Yeah. So you captured the spatially and temporary incoherent holograms. You captured three shots of holograms. Yes, yes. In the first publication of Finch, you in 2007, you used the arc lamp or thermal lamp, and you captured three-phase shifted incoherent holograms, and you reconstruct the OSA characters reconstruction image. So I would like to know what is the motivation in the recording of spatially and temporary incoherent holograms. This is because in the basic principle in Finch, so spatial incoherence is considered, and however, so temporal coherence is big challenge, I think.
The source was a white source, arc lamp, so
yes,
it was temporarily incoherent, but when you come to a grating or a grating mask with so wide spectral white light, you get the focus in different focal distances. So we added a filter, chromatic filter, to narrow the spectrum and to get quasi-coherent, temporally quasi-coherent light. That was our motivation. Because the focus was in a different, the red focus was in a different place than the green focus. So we had to use a chromatic filter. But it's all this topic is when we say incoherent hologram, we mean spatially incoherent hologram. We don't say it, but it's obvious that the light is quasi-monochromatic, mean coherent, temporally coherent light, and spatially incoherent light.
Okay, thank you.
Okay. Having more questions? If not, then let's thank the speaker again. And now our next plenary talk